My name is Greg Lendine, and I'm the Science and Operations Officer at the National Weather Service office in El Paso, Texas, and Santa Teresa, New Mexico. Our office forecasts the weather for southern New Mexico and far west Texas. And I'm here today to talk to you about global weather patterns and how it affects the local weather. This is a satellite image from our GOES-16 satellite, and it shows visible imagery that's been colorized to depict all the various weather patterns that you currently see on there. This is sitting over the Americas, and you can see various hurricanes, weather systems, clouds, open ocean, and even the smoke from our western fires on this image. And basically, the weather here, you see that some of it can be thousands of miles away, but it may be having an impact on our local weather. It's all connected. The weather you see is the result of a combination of many factors, and these factors occur on different size scales and time ranges. They include changes in climate, which occur over years, decades, and centuries, seasonal variations, which are due to the Earth's position relative to the sun. This includes winter, summer, spring, fall. Also, global and large-scale weather patterns, which occur over days, weeks, and sometimes months, and we also include local and regional effects, which occur over minutes, hours, and days, which includes daytime heating, the terrain, vegetation, and urbanization. But our focus of our talk today will be the global and large-scale weather patterns. Here are some examples that we're going to talk about today in this presentation. We're going to talk about Hadley and Ferrell and polar circulations, long Rossby waves, jet streams and jet streaks, continental and maritime air masses, El Nino and La Nina, the atmospheric rivers and monsoons, the oceanic decadal oscillations. These all can interact with each other to create kind of the weather that we see and how they impact it. Almost all weather is the result of differences in temperatures or heating between regions of the Earth, both at the local level and globally. In this example of a sea breeze front, warmer temperatures on land cause air to rise. The cooler temperatures at sea cause the air to sink. This creates a pressure difference that creates the onshore flow during the day along nearly all the coastlines. This pattern reverses at night. This concept can also be applied on a global scale due to differences in heating between the equator and the poles. Hadley cells are basically global weather at its most basic form. The equator receives more heat from the sun than higher latitudes at the poles, and as a result, the warm air rises near the equator. The cooler air from higher latitudes moves down toward the equator to replace it. The warmer air aloft moves toward the poles, and then further north, the warm air cools and then sinks to the surface, keeping the circulation going. Earth's rotation, or the spin on its axis, causes this moving air to deflect to the west, which we call the easterlies or the northeast trades. Partly due to Earth's rotation, the equatorial air does not go all the way up to the poles and vice versa. There are actually 3 broad regions of north-south circulations for each hemisphere, making it a total of 6 for the entire planet. The Hadley cell we just discussed runs from the equator to about 30 degrees either side of the equator. The Ferrell cell runs through the mid-latitudes and runs from about 30 degrees to 60 degrees, and this cell contains the westerlies, what we know as the westerlies, the movement of air from west to east. And then the polar cell is near the poles at 60 degrees and up to the north, and they have an easterly flow. In this idealized schematic or diagram, the Earth has 6 major circulation bands in the troposphere. Near the equator sits the intertropical convergence zone, the ITCZ, which is an area of rising air, active rainfall, and the source region for a lot of tropical storms. This is also the point where the tropopause is highest, with the polar region having the tropopause at the lowest elevation. At 30 degrees north, the air is generally subsiding with a general lack of weather and moisture occurring there, and it's an area of high pressure at the surface. It's no coincidence that most of the world's deserts and arid regions, including New Mexico, sit roughly at 30 degrees north and south. This image here is an idealized global weather pattern. And if you notice, it's relatively smooth flow. The real world, as we've seen from the satellite image, is much different. And the reason for that is coming. And this weather pattern here, if it stayed this way, there would not be much weather. Something is disrupting the flow that we see in this image. And what we call those disruptions, we call them waves. They start out as a small undulation or generally smooth flow, and they grow with time until they become large weather systems that provide weather across the area. We call these waves Rossby waves or long waves. There are many causes for them, but one of the more easier ways to describe it is called the butterfly effect, and that's essentially a butterfly flaps its wings in China and you have a winter storm in New York City. This is all part of the kind of the chaos theory, but really what it means is that small little disturbances start to add up and make bigger disturbances until they go to full-blown weather systems. It's kind of like the snowball rolling downhill. It gets bigger with time. Okay, these generally occur near the boundary of Faro and polar sills in the mid-latitudes, where we see a lot of our most active weather. Here's a different way to look at the Rossby waves. They start out, this is superimposed on our northern hemisphere here. They start out as a relatively smooth flow with a jet stream between the cold air to the north and the warm air to the south. As an undulation or oscillation begins, you see that the cold air is starting to slip a little bit south while the warm air is starting to move a little bit north. And then finally in the last image there, you see that there's a ton of warm air pushing well north of the area while cold air is sinking further south. This kind of develops into what we call a Rossby wave life cycle. The waves or oscillations begin to form in the smooth flow. This image that we see on the right here, we're looking down at the top of the planet from the north, looking down over North America and the northern hemisphere, as well as Asia and Europe. And the waves will deepen with time, and then eventually they become very extreme with large polar vortexes, where a lot of movement of air north and south. Eventually, some of the cold air will pinch off into a closed low and separate from the pattern, and that kind of restores the equilibrium, and then the cycle begins again. This is really the planet's way of distributing heat north and south. These waves can result in a variety of patterns. In this image, a ridge is located in the center of the country. To its east is a deep trough on the east coast. There's a lot of active weather probably happening with that trough. To the west are a pair of troughs that are linked in a more complex way and may be part of a split flow. The colored contours that you see are associated with the jets that will be discussed later. There are many different types of wave patterns that give us different kinds of weather. We'll start off here with the negatively tilted troughs. And they're called negative tilted troughs because the top end of the trough is more to the west than the southern end of the trough. And it's associated with more active weather, especially just to the east of the trough axis, pretty close to the trough. And this is where most of your active weather is. It's an area of falling pressure, rising air, and increasing moisture. You have warm air ahead of the trough, cold air behind the trough. Kind of the opposite of that kind of trough is a zonal flow, where there's almost no north-south undulation in the troughs across the country. This is a kind of a pattern with mild conditions with no real exchange of air masses north and south. There may be a little bit of weather along the front, but it's really weak and not of much consequence. An extreme form of waveform action here is what we call a blocking pattern, where you have highly amplified waves and troughs. And In this kind of pattern, the west to east progression of storm systems breaks down and they stall out and basically stay in place for several days up to a couple of weeks. These low pressure systems will cut off and just kind of meander and sometimes drift back to the west. Kind of the opposite of those blocking patterns are these waves we call open troughs, which move fairly rapidly from west to east. They do have weather associated with them, but not to the level of maybe a negatively tilted trough or a closed low. Along with waves, we also have these atmospheric jet streams. And we have two principal ones, with a polar jet stream, which kind of separates between the polar air mass to the north and the mid-latitude ferrocell area in the middle, and the subtropical jet stream, which serves a similar purpose between the mid-latitudes and the equatorial Hadley cell circulation areas. They do undulate in varying intensity as a result, and as a result will impact local weather. They act just like oceans and rivers in that there are fast-moving currents in them, and the weather systems will align with these fast-moving currents or jet streams. The jets that are formed as a result of the global cell circulations and the Earth's rotation, they occur high in the atmosphere near the tropopause. The polar jet is the much stronger of the two main jets, with speeds over 160 miles per hour possible in its core. The most active mid-latitude cyclones or storm systems will have strong polar jets associated with them. The weaker subtropical jet plays a role in the northward moisture transport into the mid-latitudes. This is an image of a jet stream occurring over the continental U.S. Note the jet conforms to the wave pattern with a deep trough over the Rocky Mountains. In this image, you could expect to see the most active weather to be occurring over Kansas and Oklahoma, right under the jet and just east of the trough axis. The jet acts as kind of a boundary between colder air to its north and warmer air to the south. Undulations in this jet will cause the air masses to move north or south depending on the orientation of the jet. Locally in New Mexico, a weather system approaches. If you are in south of the jet, it'll be dry, warmer, and windier. If you are north of the jet, you will experience cooler and wetter weather. Jet streaks are regions of high-speed flow within the jet. This change in speed will affect the general stability, lift, and flow in the region, and will have an ability to enhance developing weather patterns in areas nearby. In the image, upward motion occurs at the right entrance region and the left exit region of this jet streak. These are the areas that can have very active weather. The diagram indicates those areas where the air is rising. The atmosphere is made up of several different types of air masses that are all identified by their source regions, their moisture content, and temperature ranges. In this image, the North America has 7 such air masses that frequently interact to generate active weather across the area. Generally, continental air masses are dry and maritime air masses are wet. The further north you go, the cooler the air mass is. Many times during winter, the Arctic and polar air masses will be pulled southward, resulting in much lower temperatures in southern regions. New Mexico and northern New Mexico sit at the center of the continental tropical dry air mass. During the summertime, North American monsoon moisture will flow into New Mexico from the maritime tropical air masses from the eastern Pacific and the Gulf of Mexico. Another feature to take into account are atmospheric rivers. These are long, deep plumes of moisture that originate from a tropical oceanic source region and will extend for hundreds or thousands of miles further northward. They are pulled upward by a jet, and when they reach landfall, a considerable amount of rainfall can be expected for the impacted area. This is a satellite image showing such an atmospheric river. A long, thick band of clouds, which are indicative of deep moisture, can be seen originating from the lower right corner of the image in the Pacific Ocean and extending up toward the Pacific Northwest. This deep plume of moisture will bring a large rain amounts to the region, including British Columbia, Washington, and Oregon. Another pattern that will affects the moisture in an area is the monsoon. Now, what the world knows as the monsoon is not what we have in our local area. They have what's called the Asian monsoon. And essentially, in the spring and summer, the warm air on the land and cooler air over the ocean creates a very large sea breeze effect to some degree. But instead of being localized to the coast, it goes all the way up through the Indian subcontinent. And this flow reverses in the winter, where the ocean is warmer and the land is cooler. There's general flow out to the ocean, and it tends to be a dry pattern for the landmass. That third diagram you see there is actually this monsoon pattern. It's not really limited to just India. It also includes South Asia and China and parts of Africa. And this pattern is very important to the moisture flow in their area. Locally, we call the monsoon the North American monsoon. It is a seasonal change to a moist southerly flow in the summer. This diagram is a classic image of what a North American monsoon should look like. There is an area of high pressure to the east, an area of low pressure to the west. This sets up a southerly flow over New Mexico that pulls moisture up from both the eastern Pacific and the Gulf of Mexico that leads to frequent rainfall in the region during the summer months. This pattern did not develop this summer, with the high sitting over the region instead of being further to the east. The result was a hot, dry summer for New Mexico. Finally, I want to get into oceanic oscillations. The ocean's influence, since it covers 70% of the Earth's surface, ocean's influence on jet stream location and resulting weather patterns can be quite significant, just resulting from changes in sea surface temperatures. This image you see is sea surface temperature anomalies. The cooler temperatures off the west coast of South America are indicative of an La Nina pattern, where the blue colors represent cooler than normal temperatures, sea surface temperatures. The orange represents warmer than normal sea surface temperatures. But this La Nina pattern will result in a shifting of jet streams further north, with more dry weather expected for the southwest part of the country. Here's a schematic of an El Nino pattern, which will actually brings us wetter winters. It's characterized by warmer temperatures near the equator. The jet stream, as a result, is further south. It allows storms to track across the southern U.S., bringing us rain and sometimes winter snow. The opposite of the El Nino is the La Nina, and is characterized by cooler sea surface temperatures near the equator. It results in an S jet stream that is displaced further to the north. And with the jet stream being further north, we have a drier weather pattern across our area, especially in the winter. There are other circulations that can impact our weather other than the El Nino and La Nina. This one, starting off with, is called the Caribbean Gyre. It's a relatively new feature that's been identified, and it's relatively weak. And its main feature is that it has a big role in the development of tropical weather systems, including hurricanes and depressions. But it has a secondary impact on New Mexico and the desert Southwest, where it could alter the path of the jet, either enhancing or suppressing weather in our region. Another oscillation that occurs in the Pacific is called the Eastern Pacific Oscillation. And it has two phases, positive and negative phases. And in the positive phase, there's a large persistent flow of low pressure in the Gulf of Alaska. This has large impacts for Canada and the Pacific Northwest with a lot of active weather. Milder temperatures will occur across much of the southern U.S., And it also may allow, because the jet stream is further south, allow for a split flow that brings moisture to the southern US. The negative phase of this eastern Pacific oscillation is a persistent area of high pressure. This thing forces the polar jet far to the north in Alaska. Not only does it give mild temperatures for Alaska, but it also results in less weather for the Pacific Northwest and generally our area as well. It also results in a really deep trough over Canada and the United States that brings very cold temperatures to most of the country. One example of this was the 2011 in February when we had sub-freezing temperatures for several days. It was part of this very deep trough that occurred. Linked to the Eastern Pacific Ocean Oscillation is the Arctic Ocean Oscillation. And in the positive phase, the jet is further south, allows for a more active weather pattern across the country. Where the negative phase, you have a strong ridge along the west coast and a deep trough along the east coast, and it brings cold air to much of the east. Another oscillation is the North Atlantic Oscillation. And again, it has an impact on where the jet stream is located. And as a result, it subsequently can impact not only the east coast of the United States and Canada, but it also impacts Europe and Northern Africa. And it can have some secondary effects for us because with the jet stream being further south, it might allow, even though it's far, far away from us, it may allow weather pattern to be more active for our area when it's in this positive phase. So you generally and overall, you want to think about these oscillations as when they're a positive phase, the jet stream is further south and allows for a more active weather across land masses, where in the negative phases, the jet streams are displaced kind of further north for our area, relative to our area, and will keep weather away from our area. Well, that kind of concludes the different topics that I was going to talk about today, but in summary, I wanted to re-emphasize that local and regional weather patterns are strongly influenced by global and large-scale weather features. Quiet and mild weather is generally associated with smooth flow and with little interaction between the air masses. Large-scale features can combine to enhance or suppress a weather pattern or weather system moving through a region. Jet streams can be strong drivers of mid-latitude weather systems. And finally, the world's oceans are strong influencers on weather patterns, especially in jet stream placement, which has a big impact on local weather. I want to thank you for taking the time to view this presentation and hope you enjoy the rest of the science conference.